Warning, the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is yet another video in my series on sequences and series. And this is usually reserved for the end of that topic. And the reason why, well, we'll investigate in a little bit why this specific topic, which is the binomial theorem, is stuck within the sequences and series material within a pre-calculus course. But this video specifically is going to be dedicated to Pascal's triangle. That is such a beautiful triangle. Let's go ahead and build it. And I want you to see patterns. So most of mathematics is about pattern recognition. Let's see if you can detect a little pattern. Let's suppose we build a triangle where we write a 1 here. It's a numerical triangle. And then as triangles do, they open up like this. So let's go ahead and put another 1 right here. And let's put a 1 on the other side. In fact, you could keep doing that if you wanted to. You keep going like that. But what we're going to do is reserve a little bit of space for the filler in between. The filler in between, I'm just going to put for now a 2 there. And then the next one, I'll put a 1 on the edge, and then a 3, and a 3, and a 1. And then I'll put another 1 on the edge, and a 4, and a 6, and a 4, and a 1. I'll put another 1 on this edge, and I'll have a 5, and a 10, and a 10, and a 5, and a 1. And so on and so forth down the line. Now, a couple things that you should possibly already notice is, well, at least one thing you should possibly already notice, is that the filler along these diagonals right here, let me highlight this diagonal. It's 1, 2, 3, 4, 5, 6, and it'll go on forever like that. And there's also a similar diagonal right here, 1, 2, 3, 4, 5, 6, and so on and so forth like that. You might also notice another pattern going on that many people don't initially see, which is the next diagonal, 1, 3, 6, 10, and so on and so forth down that line. Notice the difference between 1 and 3 is 2. Let me write that down. The difference between 1 and 3 there is 2. The difference between 3 and 6 is 3. The difference between 6 and 10 is 4. The difference between 10 and 15 is 5. And that pattern will continue down the line. But how did I know, without knowing that that pattern would continue down the line, how did I know how to build out, and how do I continue to know how to build out this triangle without actually having these edges already pre-filled in for me? Let me go ahead and do this. I'm talking and writing at the same time. It's a little bit hard for me to think. So the way that this triangle is actually built is that there are 1s along the exterior diagonals, the edges here, they always have 1s. And then to build the rows, so the very first row that doesn't have, that has more than just an edge of 1 is this third row right here. How did I get that 2? Well, I took these diagonal elements, 1 and 1, and I added them together to get that 2. Same thing for the next row. I took these diagonal elements, added them together. 1 plus 2 is 3. 2 plus 1, again, is 3. And the next row I built the same way. 1 plus 3 is 4. 3 plus 3 is 6. And 3 plus 1 is 4. And you can see that pattern continues all the way down the line there. That is Pascal's triangle. It's a very beautiful triangle. There's a lot of really cool theory behind this. I have a full 2-hour video on how this triangle relates to chaos theory and fractals and the golden ratio and Fibonacci numbers. This is a beautiful triangle. But for now, let's just go ahead and fast forward one step here and see what my next question is going to be. Let's go ahead and take powers of a plus b, that binomial. Now, why would I want to do that? Well, let's find out. If you take a, oh, I need a different pen color for this, sorry about that. If you take a plus b and you raise it to the 0th power, well, obviously that is equal to 1. If I took a plus b and raised it to the 1st power, by the way, it's equal to 1 as long as a and b are non-zero. 0 to the 0th is indeterminate. So a plus b to the 1st is, well, 1a plus 1b. Let me write that in there. So notice the coefficients, 1 and 1. And then a plus b squared. Well, that's 1a squared plus 2ab plus 1b squared. 1, 2, and 1 are the coefficients. And let's do a plus b to the 3rd power. If you were to multiply that, you would get 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. 1, 3, 3, 1 being the coefficients. Now, just based upon these first few expansions, I hope that you see a strong similarity between this triangle of coefficients for the binomial expansions and Pascal's triangle. Notice those coefficients are the same, and that is not a coincidence. That is actually a fact that can be proved. Each of these rows is actually contains the coefficients of the expansions of these binomial powers. And that is really cool because often in calculus, you need to expand out a binomial very quickly. It might be some, x plus y raised to the 7th or something like that. And you don't want to have to multiply x plus y times itself 7 times. That's a pain. It's much faster actually to draw out Pascal's triangle. Let's actually see how that works, how I would actually do this in a calculus class. Now, normally this is going to be within a bigger problem in calculus, but you have to suddenly expand out some binomial to the 6th power. So what we're going to do is go ahead and write down Pascal's triangle. And I should mention kind of how the powers go on this. Maybe I should do that back at Pascal's triangle, but maybe not. I think I will though. So notice, for example, in the 2nd row, because the 1st row is kind of the 0th power, that doesn't really matter. But the 2nd row is kind of important. So I'm going to label A in red and B in green. It looks very Christmassy, even though we're nowhere near Christmas right now. Might be when you're watching this video though. Okay, so we start with A to the 1st power, which is the power right here, and B to the 0th. So that's kind of a critical note. And we're going to add 1 a to the 0th, b to the 1st. Now, a lot of people would not write it that way, but it is true that the powers on a start with the 1st power, this exponent right here, and they decrease. So it starts with a equals a to the 1st, and then the next term will be a to the 0th. And then the powers on b start at the 0th power, and they increase until you get to this ultimate 1st power. Note also that any given term here, if you were to add the powers up, let me circle them up in blue because it's colorful. If you add those powers up, it will always be, oops, that was not supposed to happen like that. In any given term, if you add the powers up, it'll be that power right there. Let's try this out in the 2nd row just to showcase what I mean. So the 2nd row, we have a plus b quantity squared. So the very first term of the expansion would be a squared b to the 0th. So I start with this power on a and the 0th power on b. And then we would add 2 times a to the first, b to the first. Notice those powers add to 2. Again, that 2 right there. Plus a to the 0th, b to the second. Now, obviously, 0th powers of non-zero bases are 1. So b to the 0th is just the number 1. So that first term should just be 1a squared or a squared. And then the last term should be 1b squared or just b squared. That's okay. It's just to showcase the pattern. I'm showing the 0 pattern or the 0 powers on there. Let's just go to the third power here just to showcase this one last time. So the third power, again, I'm using red for a. So it's going to start at a cubed and then go to a squared and then go to a to the first and then a to the 0th, even though you don't have to actually write that one in. And then the powers of b start at b to the 0th, increase to b to the first, then b to the second, and then finally b to the third. Anytime that you're looking at any given term there in this expansion, every single time you look at a term, its powers will sum to 3. Now, using that idea here, let's just suppose again that you're just dealing with this in a calculus class. The first thing I would do is just this 1, 2, 1, 1, 3. It's not that you memorize Pascal's triangle, you just build it really quickly. 1, 5, 10, 10, 5, 1. Let's see. So 0th, 1, 2, 3, 4, 5. So we need one more. 1, 6, 15, 20, 15, 6, and 1. So I know these are the coefficients of my expansion. Again, this is the 0th power. That would be the first. I'm not going to write them all. And then the second, third, fourth, fifth, and finally the 6th power, which is one we want. And here we go. I'm going to, again, just for showcasing this, I'll use red for A and green for B. And this expansion will equal 1. You don't really have to write the 1. I'm just writing it in there. And now I'm going to do a to the 6th. I'll leave some room and I'll put a to the 5th. I'll leave some room, a to the 4th. I'll leave some room. Let me zoom in so that it looks cleaner. A to the 3rd, leave some room. A to the 2nd, leave some room. A to the 1st. And then we have a to the 0th. Obviously, I'll erase that when we're done. Powers of b. B starts with b to the 0th, and then b to the 1st, and b to the 2nd, b to the 3rd. Notice the powers all add up to 6 here. B to the 4th, b to the 5th. When I say the powers of each term, and b to the 6th. And then finally, I just go to Pascal's triangle and fill in the coefficients. See, we had a 1 plus 6 plus 15 plus 20 plus 15 plus 6 and finally plus 1. Obviously, this is not the most beautiful way of writing it, so I would probably just do one last little cleanup. That's a to the 6th plus 5a to the 5th b plus 15 a to the 4th b squared plus 20, right? You get the whole idea, right? Now I can't stop myself. And rather than bore you, I actually just filled it out. So that is how you do a binomial power. Now that's a simple binomial power because it's just a and b. But what happens when you have something that's a little more complex? Like this guy right here. This looks a little more complex because, well, it has just different numbers involved, but actually you can kind of label them. You could say that a is equal to, let me use my red lettering, a is equal to 1/3 and b is equal to a negative 2x. Remember, I was writing it before as a plus b, right? A plus b to the power p. And so I would like to keep it as a plus. So I'm going to use 1/3 for a and a negative 2x for b. So that is actually a plus b to the 5th. Now, without even writing down Pascal's triangle, I can at least write down the power expansions. I don't know the coefficients yet until I write down Pascal's triangle, but the power expansions should not be too terrible. So let's go ahead and write those out. This will equal some constant, namely the number 1, times 1/3 to the 5th, and then that negative 2x to the 0th, which I'm going to skip writing. Plus, I will have that 1/3 to the 4th times the negative 2x to the 1st. Notice the powers add to 5. And then I will continue this pattern down. And in fact, like I said, I usually write all the red stuff first. Not that I write in red every single time I do this style of problem. It's just I'm writing in red right now. So, but I just write the decreasing powers. And I didn't leave myself enough room. So give me a moment while I adjust the size here. There we go. I just went ahead and moved everything down. Notice I have the decreasing powers on the 1/3. Now I'll start with the increasing powers on the negative 2x. That position is going to be negative 2x to the 0th, so I don't even bother writing it. And this will be negative 2x to the 1st. This will have a negative 2x being squared. This will have a negative 2x being cubed. Again, the powers are adding to 5. Negative 2x to the 4th, and then I have one last term back here, a negative 2x to the 5th. And then finally, now I need to add in, and there'll be a bunch of plus signs here for this, I'll add in the coefficients. And the coefficients are found via Pascal's triangle. And here's the triangle from earlier. So we see that the first row being, we'll call the top row the 0th row, and the second row we'll call the first. So it's the 0th, 1st, 2nd, 3rd, 4th, and 5th. So the 5th row, if we start with 0th, is 1, 5, 10, 10, 5, 1. So filling that in here, 1, 5, 10, 10, 5, and 1. That's a lot of color, I know. But now you're going to actually multiply out those numbers. So here we go. We're going to clean this up. 3 to the 5th is 243. So this is just 1 over 243. 3 to the 4th is 81. And then we have a negative 2 and a 5. So it's negative 10 81sts. I'll write that in there. Minus 10 81sts x. Notice that negative is starting an alternation is what we would call that. 3 to the 3rd is 27. And then negative 2 squared is 4 times 10 is 40 27ths. So plus 40 over 27. I would reduce these if they are reducible, but these are not reducible as of yet. And in fact, they won't be, that I'm looking through all these. The next one, let's see, the numerator is going to be a negative 8 times 10, or a negative 80 over 9. And that's x to the 3rd. And the next one, let's see, we have a negative 2 to the 4th, which is a 16, times 5 is 80 over 3. So plus 80 over 3, x to the 4th. And you'll have to watch my arithmetic. I can sometimes make little silly mistakes. And then finally, negative 2 to the 5th is negative 32. And then you have x to the 5th. I'll quickly check my arithmetic. Everything looks good to me. So that is the expansion of that binomial. And it is actually, once you get used to it, a lot faster than sitting here and multiplying out 1/3 minus 2x times 1/3 minus 2x times 1/3 minus 2, and so on and so forth down the line. It's just a lot faster to do the binomial expansion via Pascal's triangle, at least so far. I say at least so far, it sounds like it's a threat. It's not a threat at all. I'm just saying that right now it seems as though this is going to be faster, and it actually is. Now let's see what you'll actually deal with in calculus. In calculus, you'll deal with this style of fraction. You know this as a difference quotient, and In fact, in calculus, you'll see this on here. It's a limit as h tends to 0. That's the only difference between what you've been working with and the calculus notation, is that we're allowing h to get infinitesimally close to 0. So you essentially are looking at something nearing to x to the 6th minus x to the 6th upstairs, which is tending to 0, divided by a number that's tending to 0. So you have 0 over 0 or something tending to that. And normally you would not be able to compute that. But as I tell my calculus students, always perform your arithmetic before algebra, algebra before trig, trig before pre-cal, and pre-cal before calculus. Calculus should be your last step when you're working with mathematics. And so, or at least at this level. So what you want to do here is any type of algebraic manipulation you can. And here, actually, this, you can use a difference of squares or a difference of cubes as well to help out with this. But I like the idea of just using the binomial expansion, using Pascal's triangle. Again, I know that this is going to equal, let me just draw out a large fraction with a minus x to the 6th on the back end and h downstairs. And you will have x to the 6th, then x to the 5th, then x to the 4th, then x to the 3rd, then x to the 2nd, then x to the 1st, and you'll have a space there for the x to the 0th. As far as h's, you'll have h to the 0th, h to the 1st, h to the 2nd, h to the 3rd, h to the 4th, h to the 5th, and finally h to the 6th. And then you fill in the coefficients via Pascal's triangle. And you see the 6th row there is 1, 6, 15, 20. 1, 6, 15, 20, then it starts to decline. So 1, 6, 15, and then 20. And then it starts to go back to 15, and then 6, and then 1. And what you can do with this in calculus, again, is you can cancel any like terms. Well, there's only two like terms, x to the 6th and a negative x to the 6th. But then you can see that in the numerator, an h can be factored out. If you factor out an h in the numerator, you get 6x to the 5th plus 15x to the 4th h plus 20x cubed h squared plus 15x squared h cubed, let's see, plus 6x h to the 4th plus h to the 5th. All over h. And those h's cancel beautifully by eraser. And so by power of whiteboard, we get to this point right here. A very, very nice problem. Like I said, there is another way we could have done this, and I cannot, it's a missed opportunity if I don't show you the other ways we could have done this. For this specific problem, we might as well just see, what are the other ways we could have done this? He keeps saying there's another way. What's the other way? The other way is looking at this as a difference of squares. So let me just put in a big line there. We could have said, oh, that's like x plus h to the 3rd being squared minus x to the 3rd being squared over h. And you could do a difference of squares there. But you still have an issue, because that's going to be x plus h cubed minus x cubed times the quantity x plus h being cubed plus x cubed all over h. And each of those is a difference in a sum of cubes, or respectively, they're a difference in a sum of cubes. So the difference of cubes, let's get right here, you could have written as, I'm an algebra geek, I like this stuff, x plus h minus x times the quantity x plus h and quantity squared plus x times x plus h plus x squared. And then the next one would factor to x plus h plus x times the quantity x plus h squared minus x times x plus h plus x squared. It is a trip how often in calculus you have to reach back to old algebra skills, and this is a good example of that. Notice in all of these, things cancel, at least not all these, but two of the factors upstairs. These two x's right here cancel beautifully, and you're left with just an h upstairs, and the h's again will cancel. But then in this case, you would probably want to clean things up and maybe even multiply things back out if you could. So that is the problem with the difference of squares or difference of cubes approach, is that it doesn't leave you with a nice clean form, even though most people would probably not call this terribly clean, but actually it is a very clean form in calculus, because you're going to allow h to go to 0. And if you allow h to go to 0, that's just 6x to the 5th. It simplifies down quite a bit. So anyhow, just a good example of what you run into typically in Calc 1. Now, I love this topic. Even though I don't use the binomial theorem that much, I love Pascal's triangle, and I love this topic for a very specific reason. So I'd like to see if you understand why we're covering Pascal's triangle right after sequences and series. It just kind of doesn't make sense. But in reality, it's a really good point to talk about Pascal's triangle. So let's go ahead and revisit Pascal's triangle really quickly. So there is Pascal's triangle, or part of it, right? It goes on forever. And what we're going to do is relate it to something we learned before. I'm going to take each of these rows and I'm going to slide them over to the left. So taking each row and sliding them over to the left. And the way I'm going to do this actually is I'm just going to pause the video and do that. Okay, so I have successfully slid everything over to the left. Now what I want to do is just highlight some rows here. Actually, not even some rows, some diagonals. So I'm going to highlight that diagonal right there, and I'll use alternating colors here. I'll highlight this diagonal, and then I'll highlight the next diagonal, and I'll highlight the next diagonal. And at some point my highlighter is going to be too thick here to do this, but I'll just continue as long as I can. All right, I think that's pretty good. So let's go ahead and take a look at these diagonals. Why did I highlight them? Well, if you add up the numbers in those diagonals, you'll get 1 in that first diagonal, 1 in the second diagonal, 2, right, 1 plus 1, and then 3, 1 plus 2, and then 5, 1 plus 3 plus 1, and then 8, which is 1 plus 4 plus 3, and then this one, 11 plus 2 is 13, and what is that, 21, and the last one there is 25, 26, 27, 34. I don't know if you remember from a previous video on sequences, but we ended up talking about a very famous sequence called the Fibonacci sequence. And that is exactly what gets developed by the diagonals of this summation, or the sum of these diagonals. That is only part of the reason why this is a good fit in the sequences and series material. The Fibonacci sequence is incredible. And it, like I said earlier, it's tied to Pascal's triangle. You see it right here. It got tied to Pascal's triangle, and it gets tied to chaos theory, and it gets tied to the golden ratio, and all that fun stuff. So it is a really, really cool topic. And if you haven't had a chance, I have a video on my channel, and let me see what it's titled. You can see it right here. It's called CRC Math Awareness Week, the Golden Fibonacci Numbers and Chaos. And actually right here, this is actually a really cool game called the Chaos game, where you're taking Pascal's triangle and you are, oh look, actually I just did it in that video right there. I did the whole slide over and created the Fibonacci numbers just out of Pascal's triangle. But if you take Pascal's triangle and remove the even numbers, you end up getting, let me see if I can fast forward it slightly, just because I think it's awesome, but you should watch it. So if you take all the even numbers out of Pascal's triangle, you get a really cool pattern. And then I highly recommend just watching this video. It's 51 minutes in, and you'll see what happens at the awesome aside. Anyhow, that does it for this video. And in the next video, we'll continue this conversation by going into factorials and combinations, a little bit of probability funness in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.